Welcome everyone to today's training event. Us at Heartland Exchanger, we're trying to do monthly training events and make sure it's very client specific. So we sure greatly appreciate y'all joining us, as we know how busy y'all are and how valuable your time is. We definitely don't want to waste your time here. So the OPF guys have jam-packed a ton of info into this hour slot to ensure you guys all walk away fulfilled. My name is Garth Govern. I'll be your host for today. I'm the GM of Heartland Exchanger. I'm stationed here in Fort Saskatchewan, Alberta. I've been with the company now for over 22 years now. And our featured presenters today from OPF are down in Chattanooga, Kansas. These are three of OPF's finest engineers in Eric Phillips, Jonathan Burchett, and Sam King. So if you all could please mute your mic and shut off your video, we'll get the show on the road here. We'll probably be finishing up the training about 10:50 and give us 10 plus minutes to answer questions. So if you have to leave, you can go ahead and leave. If you want to stick around and hear more of the answers to any excess questions, you're more than welcome to stay on and go over with us. We appreciate and welcome your questions greatly. So if you can put them in the chat or verbally ask at the end, and then we'll answer all the questions at the end. All right, and the guys will be glad to answer them. So to start things off, I'll tell you a bit more about Heartland Exchanger. I know a lot of you guys really good, and you know my history, but I know we have a lot of new people on here too. So I'll just share my screen here. All right. So this is Heartland Exchanger. These are the companies as an agent rep company. These are the ones we're working with to help us find solutions and services to the different applications. So how we know most of you all is with our Alpha Laval line. So Alpha Laval is world known for their plate heat exchangers and their different styles of plate exchangers and their high efficiency of plate exchangers, either in a spiral, compa block, plate and shell, gasketed units, whatnot. And then for shell and tube companies, we got Hughes Anderson out of Tulsa. Our smaller units, we use ACE out of Ontario. Watco out of Quebec is our electronic heat exchangers. SGL Carbon out of Cleveland is our graphite exchangers. And then with heat transfer, we're always getting into solutions on making sure we can get long run times. So we got companies like ATB Systems that has a fabulous backwashing valve to reverse flow to keep your heat exchangers clean. WTR has a ball cleaning system that is fabulous for keeping a heat exchanger clean while it's in service. These balls are cleaning your system. Also, back to that ATB, they have an online system too with brushes. So they do that reverse flowing valve with brushes, so we can keep a heat exchanger clean on the tube side in service with brushes or balls. We're very strong in chemical cleaning. It's one of our specialties. Orange Tech here is online ultrasonic cleaning, so really good technology that we're bringing into Alberta. We got a couple really good installations where we're using ultrasonics to keep your heat exchanger clean. So I think you guys understand where we're coming from, where we got a lot of good options and ideas to put in the right heat exchanger. And once the right heat exchanger's in, we're making sure it gets the longest optimal runtime. And then obviously furnaces is part of the heat transfer business of the processes out here. So we were so grateful and thankful to be able to meet up with Rob Phillips and his company out of Chattanooga, Kansas. And so that's where we're at here today. So I'm going to stop sharing here now. And without further ado, I'm going to pass the mic over to the guys in Kansas. Since we've brought OPF on board, we have been so impressed with their professionalism, their knowledge, their quality, that we're very proud to represent them out here in our territory. And they know they can help a lot of you guys with your projects, and girls with your projects and your issues with your furnaces. So Eric, Jonathan, Sam, I'll let you guys introduce yourselves and you know, tell a little bit about your background before you get into your meat and potatoes there. And yeah, take her away.
All right, we're getting our presentation pulled up, and in the meantime here, my name is Eric Phillips. I am here at OPF. I'm a process or sales engineer. So ultimately, I'm one of the people that receives customer inquiries and then designs the heater around your specifications and your process needs. And it's a group effort, but we end up getting you guys your quotes. So that's kind of my current role here. Sam King's in a similar role. I'll let him introduce himself as well.
And my name's Sam King. I came to OPF after a stint in the oil field, doing oil field services, fracking mostly, and found Kansas much to my liking. I do a little bit of troubleshooting, and I'm the token chemical engineer around, so I handle a lot of the process issues.
There you go.
And good morning. My name is John Burchett. I'm the Vice President of Operations here at OPF. I'm primarily responsible for the mechanical side of things. So once Sam and Eric have worked through the design for your process equipment, it's up to my group to essentially fabricate and deliver that equipment to the field. So we're incredibly happy to be here with you today, and really want to thank Garth and his team for allowing us to present this information to you.
So just a quick run through here. OPF, we do obviously direct fired heaters. That's our main line, and then we also do waste heat recovery units. We get involved in air preheat systems and SCR units to match with our heaters as well. So we're going to try to, there's a lot to cover obviously, but we're going to try to cover each of those types of equipment in this presentation. So we're going to start off here with our direct fired process heaters is the most broad terminology for these. So we're going to blow through a couple just quick applications between refineries and gas plants, talk about some heater arrangements, cover both process design, and let John talk about mechanical design and fabrication. There's a lot of back and forth on API 560, which is the standard for fired heaters. So we'll very briefly discuss that. In the midstream gas plant area, we also offer midstream style package heaters. And then last but not least, waste heat recovery units, which we've had a lot of activity with those up in your area here the past year or two especially. So most of our tried and true larger units are directed towards refineries. Since that's what we started as a company before my time, but in 1972, we hit the refinery market hard following API guidelines. So we have a lot of equipment in the field, and there's a lot of different names for the different processes and different heaters. But this list here in front of you is just a few more of the common ones. A lot of crude heaters, vacuum heaters, reformer feed heaters, air heaters, and like I said, there's many other names that I would need a lot of slides to cover all the various types of heaters. We also have gas plant, natural gas production type heaters, and those are more commonly, if you scroll through them here. Regen gas heaters, simple hot oil heaters, fractionator heaters, and then north we see a lot of glycol heaters as well. And as I'm talking, John and Sam may chime in, of course, too, so you don't have to listen to my monotone voice.
Yeah, well, and as Eric said before too, our core business starting out was direct fired heaters. We'll emphasize towards the end here, we have a lot of application for waste heat recovery units, and any type of, we'd like to be, or at least have an opportunity to look at any heat transfer opportunity that you might have that's related to a process, or even we're seeing a lot more these days projects where people are trying to capture that waste heat instead of letting it go to the atmosphere and be lost, trying to improve efficiencies a little bit, especially off turbines and things like that, putting a waste heat recovery unit on the back end of that to capture that exhaust gas and then preheat either a process fluid or a hot oil.
So on the fired heaters, there's several different arrangements. As a lot of you know, the heat source is the burners, and there's a lot of different layouts for the burners. The most common is just having floor mounted vertical firing burners. You see on the left with the coil on the outside of the flame, and then in-wall fired burners. So you're firing on the ends, and then sidewall fire. These are pretty self-explanatory terms here, but the pictures are good representations of the arrangements. Then for just the heater coil, there's vertical cylindrical heaters where you have the serpentine coil that you see there. There's helical wound coils, and then there's also serpentine horizontal coils you see in the lower right hand. And on some processes, they require arbor coil, which is a U-shaped coil, a lot of passes, and there's a large manifold that ties all of the passes together.
You usually see those with large process requirements, extremely high flow rates, very low pressure drops, high temperature requirements.
And that's one of the things I think that Eric and Sam focus on a lot, is working with you when you have heat transfer needs, is trying to determine what's the most economical arrangement for you that fits your process, and also what's the most economical in terms of a cost and a site footprint. We like to give you multiple options and work through those during the inquiry stage to make sure that you're getting a piece of equipment that is going to meet all of your needs for an extended period of time.
I'll let Sam chime in here especially, but there are some things to consider with your arrangements. As John said, some types of heaters or arrangements are more economical than others. Some processes require or lean towards a typical arrangement of both the burners and the coil. And then, as John mentioned, the footprint of the heaters varies with what type of heater we're looking at.
And that choice really is highly situational. It really depends on your plot space availability, the ambient temperatures, ambient pressures, the process itself that you're trying to work with, the temperatures you're working with, everything that's involved there can change what you really want to try and cram that into. And what's going to give you, we like to think that we're pretty good at getting you the best bang for the buck, and sometimes that'll change. Now, there are a lot of processes that don't really care what they get crammed into. A hot oil heater, a regen gas heater, for the most part, you can put it in a VC, a vertical cylindrical, you can put it in a horizontal cabin, you can put it in a box heater, or just about anything else, really. But some of the things that really do help think about what you're trying to do with a heater is with a VC, the nice thing about those is that they're inherently symmetrical. So it's perfect circles, so your heat's radiated again in a perfect circle, and you can match burners to pass configurations, and that makes it easy to maintain even heat across the entire surface. And it also means that you've just got that simple can, a convection box maybe on top, and a tall stack, And it means your plot space is really minimized. So if you've got a small area to work with, we put these on barges and anywhere that you just need to cram in a large amount of heat into a small area. And they generally are the lowest cost heater as far as an API style heater is concerned. Cabin heaters are sort of a go-to for anything that needs to boil and upflow configurations. They tend to have slightly lower pressure drops. You tend to have better in-tube pressure control. They cost a little bit more because you've got intermediate supports that you have to work with. There's a bit more steel. And you've got your box heaters that are much better at hanging a center set of coils with burners on either side. That lets you really lower the peak flux rates and lets you keep your process from overheating, which is important. You don't want it breaking down when it's not supposed to.
Real quick, back to this slide, just to give you a better representation of the arrangements here. The far left is a vertical cylindrical heater. It's just a round can with a convection section and stack on top. Here's a cabin heater. Cabin because it has this hip section, so it looks like a cabin. Helical coil, it can be laid down horizontally, or it can be vertical helical coil. And here you can see the upside down U is the arbor coil type heater.
You see, like our go-to design often will be just a VC to start with.
Most common heater.
Most common heater you get. It's a little less expensive. It's easy to work with and design, and it fits in most of the applications that you're going to want to work with. We see a lot of those in reformers, and hot oil heaters, an awful lot. NHT feed heaters. Now, once you start working with vacuum heaters, we'll tend to want a box or a cabin where you can control the precise pressure drop by elevation as you move up or down the sidewalls. Crude heaters, reboilers, you see a lot of those in cabins. And also, as you get very large duty requirements, we've built everywhere from less than 1 million BTU heaters that we kind of chuckle about making hot water heaters, and several hundred million BTU. And you'll often see box heaters are really good at, then you can put multiple cells together, get several hundred, and you have much better control of your combustion and your process.
Let's see here. Is that other stuff going to pop up?
No, you should click on it and it'll pop up.
Okay. Sorry about that. So the different components, it's kind of hard to depict it all in one slide just because of the different heater arrangements, but here's, we're talking about a vertical cylindrical VC heater with floor fired burners. The burners are providing the heat for the process. They radiate the heat. The tubes are vertical around the circumference of the heater. And then the flue gas flows up into the convection section where there's bare tubes for the bottom 2 or 3 rows, absorbing some of that radiant heat, and then switching to convective heat transfer. And then above the roof tube, there's fin tubes. That is purely a convective heat transfer. The process typically enters at the top of the convection section and exits the radiant section, so it's a counter current flow for heat transfer. Another way to differentiate between different processes for the overall heater design is forced draft versus natural draft. Historically, probably most have been just natural draft, where you have a large stack on top, which provides that natural draft to make up the pressure drop across the convection bank, and maintains negative pressure in the firebox so that the burners are able to operate natural draft. Lately, there's been a lot of interest in forced draft. So forced draft, you don't need as tall of a stack because all of the air side pressure is provided by usually grade mounted fan pushing air to the burners. And at the same time, we typically design the stack to still maintain a negative pressure in the firebox, but all the air going to the burner is pushed by a fan.
And with the small packaged heaters, you'll see some positive pressure applications. Usually we try to maintain a negative pressure in the entire heater so that you don't have any hot gases that are escaping, but it's not absolutely necessary. And when you're really trying to get a simple economical unit, we'll move over to a packaged forced draft unit with a little positive pressure, usually about ½ inch.
And we're talking midstream small heaters,
Right.
not refinery heaters. They like them to be negative pressure. So, let's see here. One quick thing to cover: the cold-in approach, which we might get into in a minute. One thing to consider with your process design is the inlet temperature of the process, as well as how efficient your heater is running, which would set the outlet temperature of the flue gas.
Right.
If the outlet temperature of the flue gas gets too close to the inlet temperature of the process, then you kind of run out of wiggle room on your thermodynamics, where you're going to run out of heat to heat the process. And what happens is the very top near the colder flue gas is starting to lose heat rather than absorb heat. So the lower the inlet temperature of the process typically means the more efficient you can make your heater.
And the easier it is to take up heat at all. And for example, when you're trying to figure out how much, what you're going to land on with your air permit, how much fuel you're going to use, and you're trying to figure out your efficiency, you need about for 85% efficiency, you're generally looking somewhere around 450 degrees at your flue gas outlet. But if you're coming in with a 600-degree process, you can't get down that low. You're never going to hit that number. And we've got other ways to approach that to get those numbers down. But just from the get-go, the lower that temperature is, the easier it is to take up heat. So the smaller the unit can be, the less expensive it is, and the higher efficiency it can be.
Yep. And I think some of the other applications that we've utilized before too for efficiency, we'll talk about a little bit more further down in the presentation here, is air preheat systems. And also we've got some multiple processes potentially in the convection box where we could utilize a process stream and then above that coil, potentially a steam coil or a boiler feed water coil. Yeah, those types of applications where, again, you're trying to maximize the amount of heat you're removing from the combustion flue gas and trying to deliver that to a system that you can utilize within your facility.
And you have a nice couple pictures here of a horizontal cabin here, I should note. I get in trouble because I forget how many clicks there are. So we've talked about the burner firing rate, that's the heat release. Lately for emissions, the floor firing density is a hot topic. So the burner floor where the burners are mounted, you divide the heat total firing rate by the floor area to get your volumetric heat release, or sorry, your floor firing density. And lately, burner vendors have been pushing for more area on the floor just to help with the natural flue gas recirculation coming down the walls and then towards the burners. That helps reduce the NOx generation with that mixing. So floor firing density is definitely something we're looking at on current heaters. API 560 requirements have bumped up that area requirement as well. I
was just going to say, I think especially with ultra low NOx applications, Eric stated, the burner manufacturers like to see good mixing. And with that recirculation down the back wall, that's one of the things, as Eric stated, that they're really trying to focus on.
Let's see here. And then for the convection section, some common terminology here. We talked about cold-in approach, and countercurrent flow. So the flue gas is flowing up vertical through the convection section, and as the process inlet is at the top of the convection, flowing down for that countercurrent flow. The effective tube length is just the tube length inside of the convection section. On fired heaters, the convection tubes penetrate through the end tube sheets, and that's where the return bins are welded on. So some of the pipe length sticks out, but The effective tube length is the area of the tubes inside the convection section absorbing all that heat transfer. Corbels are on the sidewalls, so another thing to talk about, the tubes in the convection section, the rows in the convection section are staggered, so they're offset each row to help the flue gas, I guess, properly flow up through the convection section.
And
there
channeling. The corbels are mostly, as you've got a staggered configuration for your tubes, so you don't want these open areas on the side where the tubes are offset to channel anything, and then the corbels just block the flue gas flow.
There you go. As John talked about there, we can, and in this picture shows here, there's a main process at the bottom of the convection section, but we also have capability of putting in an extra row or two if your plant needs some steam generation or boiler feed water through there, treated gas. Small processes like that you just need to pick up. I mean, usually not a lot of heat, 1 to 5 million at most.
Usually you want to keep it as a smaller function of how much total heat you're getting, because you want to be able to actually nail the process that you're targeting.
Yeah.
And we can do multiple processes up there, steam generation, boiler feed water, treat gas, and interlace if we need to, but we always want to make sure you've got enough heat to get you where you want to be.
So on specifically the process design, I'll briefly go over that. When we receive inquiry from you guys, especially for a two-phase or a vaporizing process, there's some things that we really need, and one of those is a vaporizing grid, whether it's D86 curves or TBP curves. This link here, hopefully if I link open it, never mind. I'm not sure it's actually going to open it with this thing.
With
that's
that
okay.
software.
We just need, like we show here, some properties. Usually we need some physical property grids that show the property curves, whether it be conductivity, enthalpy, densities, and then the vaporization from the process inlet to outlet. And then on the right, the data sheets that we provide with every single quote, they'll show your flux rate in the radiant section, and then the pressure drop, probably should have talked about the fouling factor as well.
It's worth mentioning this data sheets are on API 560, and when you're not sure what you need to give us, specifying a heater, really filling out this front page and maybe the next page, the first 2 to 3 pages as much as you can. The first page is really the most important. If you can give us how much duty you need and a little bit about what's going into it, we can figure out the rest, and we can talk you through whatever else you need to do.
Go ahead, John.
We're going to talk a little bit now in this section. We'll be brief here, talking about normal operation overview, specifically talking first about furnace efficiency. Sam has a few slides here. Once we're gone through those, we'll talk to just a little bit about adjustments that can be made to your fire heater to improve efficiency, reduce your fuel consumption, those types of things, and then finally talk a little bit about some emissions considerations there. So I'll turn it over to Sam here.
And of course, you want your furnace to run well. You want your furnace to, you don't want to use any more fuel than you absolutely need to. So you find that efficiency is related to how much you're firing, how much heat you're taking up. And by definition, it's how much heat's actually getting into your process. If it's not getting where you want it to go, then it's not any use to you and it's wasted heat. So as you increase some things and decrease others, then you get higher and lower efficiencies. One of the primary things that you can control once you have an established unit on site is how you handle your air control. The more air you put into your furnace, the more air you have to heat up, the more fuel it takes to get it hot. And 2/3 of your heat is taken up ballpark in the radiant section. So, and heat's a 4th order, radiant transmission's a 4th order relationship to temperature. So the hotter it is, every degree matters. The hotter you can get it, the better you're going to transfer your heat in that radiant section. So, go ahead. The relationship here,
More about thermal efficiency as it relates to, the more air, as Sam stated, more air that you're heating that's going out the top of or going out the stack and not being consumed by your process, the less efficient your heater is. So,
and that's what you find is that as you, if you've got an oxygen analyzer on your stack, just a few extra percent of oxygen in your stack can readily knock off a couple of percent of efficiency as well. So that's all heat that you're not keeping in your process. Fuel that you have to burn, fuel you have to handle, and if you're buying it, it's all dollars. So and we're just looking here at a flow chart for how to adjust a natural draft heater. And it really boils down to you want to lead with turning down your fuel or turning up your air. Being safe, you always want to have less fuel than air. You never want to get to a point where you have too much fuel in a firebox and not enough air to burn it. So if you're having trouble with a furnace, you turn down the fuel, let it stabilize, and you follow this flow chart. Just checking your oxygen, making an adjustment as you go. And you'll also note that as you get too much oxygen in, your flames will change color. Now, it depends on exactly what's in your fuel, but natural gas, generally you want a blue flame. If you've got too much air, you're going to see some yellow flame, a lot like a Bunsen burner.
Moving on to the most important, or what I think is the most important, is the mechanical design here. I'm sure Sam and Eric will disagree, but we talked a little bit primarily on the mechanical side. We're concerned with these primary factors here. One being the design temperature and pressure, which meets your requirements in the field, which in turn dictate what our tube wall thickness is, depending on the specification that we're using. And this typically ASME or API are the two primary governing design codes that we use for determining our wall thicknesses. Additionally, when we move more into the mechanical side, we'll look at stack design. Typically, for most direct fired heaters and even some waste heat recovery units, we'll have a self-supported stack. So our structural engineers look at stack vibration, look at the tube support system associated with the heater, the insulation system. We'll work in conjunction with the process group here to determine the best type of internal insulation that's required for the job. We're also looking at access in terms of ladders and platforms to get to your instruments and controls that may be attached to the heater. So those are just a few of the things mechanically that we're trying to that we look at throughout the life of the project. And here you can see on the mechanical side, we just talked briefly about the design temperatures and pressures and the tube wall thickness. Many of you probably know Barlow's formula. That is the primary formula used by ASME and API to calculate tube wall thicknesses based on the allowable stresses at whatever your design temperature and pressures are. We can back into a tube wall thickness that's required, whether that be a standard wall, Schedule 40, or a heavier wall, depending on your process application. Again, looking at the stack, that's one of the main focuses. The last thing you want at your facility is a stack that's moving in the wind. It gives you an uncomfortable feeling that something bad potentially is about to happen. And the last thing you want is a customer walking in the door saying, hey, I just saw your stack moving out front. So typically any application in Canada, we're going to utilize the Canadian Building Code. We also can use ASCE 7. The most current code right now, I believe, is 716. In conjunction with that, ASME also has a steel stack design recommendation called STS-1. So we use that as well to design the stacks to make sure that we don't have any type of vortex shedding that may result in an issue with the stack, which typically involves strakes being attached to the top of the stack. A lot of you in your facilities or as you're driving by facilities may notice these spiral wound strakes that are around the top of flares or these unsupported stacks that help with reducing the effects of that vortex shedding. As we're moving down, as Sam stated before, with the check sheet that we have in terms of, or the flow chart, excuse me, for good operation or determining good efficiency for your heater. If we're adjusting pressure inside of the stack or airflow, the two primary things that the tools that we have at our disposal are stack dampers and burner air registers. The stack damper is predominantly used, excuse me, to adjust pressure inside the heater, and these air registers on the burners are to adjust oxygen. Mechanically, I'm going to turn this back over to Sam and let him talk a little bit about supports.
All right. We've got, now as we design these furnaces, one of the things we try to do when we're saving you money is there's particular stress points at which the individual tubes have a tension or a compression on them that you need to have additional hangers on them. And so we'll design around those values. API has specific requirements, ASME has specific requirements, which are very honestly, the Canadian building codes and requirements are very, very similar and often just simply reference ASME. So that's one of the things you'll find as we limit various sizes. We try not to go taller or wider or however longer to accommodate those, but we can build them however big we need to.
Tubes generally, horizontal tubes such as the convection section or horizontal cabin heaters. I'm sure a lot of you are familiar with the general rule of 35 ODs for unsupported pipe length. And then for vertical tubes, I think API limits it to 70 foot straight tube length.
It used to be 60.
And I think they have an unsupported length as well, vertical, but OPF uses our own internal calcs for those stresses for the vertical tube supports. All of our heaters are internally lined. I think John may talk about that in a minute as well, but API 560 specifies a casing temperature, external casing temperature of 180 degrees Fahrenheit. So typically the radiant section is insulated with ceramic fiber blanket, convection section as well. Typically, occasionally we come across some customers who want insulating castable refractory, at least in the convection section. It's more common if anyone up there is firing oil, if they have soot blowers in the convection section, you want castable to avoid the soot blowers knocking off the insulation. The radiant floor and around the burners is typically 6 to 8 or 10 inches of castable refractory, and then there's also a layer of fire brick to protect from the extreme temperatures down there around the burners.
It's a good segue into our next slide here, talking specifically about burners. Again, there's been a real focus on ultra low NOx or low NOx burners as well, and the burner manufacturers have gotten very good at designing these burners. Some typical things here that many of you may know. We've got fuel gas piping going to each burner. We typically have a sight port on the burners, as well as an air control handle, which will allow you to adjust the opening for combustion air being pulled into the heater with the stack effect there. For the most part, a lot of these designs are very similar, but again, it's just and the main thing. Again, it gets very congested mechanically underneath the heater with all of the piping and access viewports that are necessary. So from a mechanical design perspective, that's always something we're aware of, and we tend to work with the end user to make sure that we're meeting all of their requirements.
So accessories of the heaters, it's real common over in Europe. There's some heaters there's a lot of heaters that we've retrofitted with air preheat. It's doesn't seem as common, but sometimes there are still units, large units, where our customers want us to design an air preheat system to go with it. So I'll let Sam briefly go over that and the benefits of air preheat systems.
Well, the way air preheaters work is, of course, all your extra heat that you can't pick up. And we talked about how a hot process will keep you from being able to get your efficiency while the rest of the heat goes out in your stack. The way that the furnace works, of course, is it heats air up, and all of that air radiates heat or has a convective heat transfer coefficient it uses to pass through fin rows, etc. That's where you get your heat from. So you use fuel, and your efficiency is based on how much fuel you have to burn. So what we do is after that stack, all that flue gas, hot flue gas hits the stack, then you'll use some sort of form of recuperative or regenerative heat transfer to heat up the incoming combustion air. So it gets really hot, a couple of 100 degrees, and now you can target 90–91% efficiency, which is awful handy. It's the biggest drawback, honestly. You've got footprint considerations. There's a significant amount of equipment involved. You can see balanced draft, induced draft fans, forced draft fans. And the cost is such that you generally don't see these on anything much smaller than like a 30 megawatt heater.
Another thing with emissions being a focus point in our industry is selective catalytic reduction units, SCRs. There's been a lot of new heaters who really want these. Similar to an air preheat system, we can duct these down to grade, but we have a lot of heaters down in Texas, along the Gulf, a few behind us in these pictures here actually, that we have mounted the SCR in the convection section, which saves on your plot space and is usually a more economical way of doing it. It just means that we have to mount an ID fan on top of the unit because the SCR induces a lot of pressure drop through the catalyst and injection system, but it results in a substack, and your ID fan on top of the heater ends up providing sufficient draft to the heater firebox, keeping negative draft. So I don't know if you have anything else to add on the technology, but
when you're interlacing, the nice thing about putting your SCRs in your convection box is you get to really dial in what temperature it operates. The catalyst that's involved usually is going to operate at between 500 and 800 degrees Fahrenheit. And sometimes you're looking for a higher efficiency heater. It's going to be too cool at the outlet, or you're going to have a big turn down, that sort of thing. And it really helps dial in the temperatures by putting it into the convection box, and it's real handy. By the same token, of course, you can't bypass. It's a lot. If you duct down to grade, it's a lot easier to bypass and operate at natural draft without the SCR functioning. And of course, maintenance is much simpler.
And I think we're starting to see a lot more focus on emissions over the last few years, and it's only going to become more scrutinized, I think, as we move forward. Right now, again, there's a lot of attainment areas around the Gulf Coast as well as in California. Those seem to be the most heavily utilized areas for SCR systems, but we're starting to see that grow just due to a lot of companies' emissions goals that they've set for themselves in the coming years. So we expect to see a pretty good rise in the use of SCR systems.
Usually we're talking NOx reduction, but there are also CO catalysts, of course. Yeah, these big ones here, like such as the one in the picture, is NOx reduction.
Yeah. Moving on to a little bit about fabrication, especially in Canada. We do have shops here in Kansas and the Oklahoma area that are CWB certified on many projects. That's important. And so we have that capability here to provide CWB certified equipment on the structural side. And then on the pressure parts side, typically ASME is the standard that's used here for any pressure piping of that sort. As you can see here, structural welding, typically most of our codes are related to CWB or ASME AWS D11. Refractory installation, again, typically is installed per API standards. API actually has a 936 standard that specifically deals with refractory installation. And then paint application, of course, is always done per the manufacturer's recommendations and approved procedures prior to the start of any of that work. Again, once things are done, of course, all equipment that we send to Canada comes with a CRN number specific to the province that it's located in. And depending on the customer's request, we also have the ability to provide Section 1 and Section 8 code stamps as well for the pressure parts.
So we're getting close on time here. So I just want to briefly touch on our midstream style heaters. They're pretty common down here in gas plants, West Texas, Oklahoma. They're not your typical API, full-blown API refinery heaters. We joke we need to come up with a better name, but we around here we typically just call them horizontal helical coil skid mounted heaters.
These are good applications they're really cost effective for an application maybe, where you're maybe not planning to have the life cycle of 40 to 50 years that you typically see in a refinery. It's an application where if you want 20 plus years, good applications too are what I call simple applications like hot oil heaters, regen gas heaters, things where it's they're consistently on, or it's a process that's very predictable. And these are very good applications. They're very very economical for any type of heat transfer application. And we try to, again, one of our focuses is to provide you with a quality piece of equipment at the least cost.
These units are arranged such that they're a forced draft design. There's just a single burner mounted on the end wall, firing horizontally. We can do low NOx or ultra low NOx down in that 0.028 pound per million BTU range. We mount a forced draft fan right on the skid with the heater. And then we mount the BMS and field train behind the heater or even attached to the heater to minimize the footprint of the unit. The instruments controls is something we haven't really touched on. OPF doesn't do the instruments and controls in-house. We rely on a handful of subcontractors or sub-vendors to provide the BMS, the field train, the valves, and the skid for the designated field system.
And the question did come in. B149.3 is fully accommodated. We have several vendors that we work with, and we work with all of our controls vendors closely to meet the requirements. B149.3 is the standard for Canadian applications, and we do meet all of those. Whether you need a PLC or simple controller or whatever your applications are, CRM requirements, low temperature requirements, we will meet all of those.
Yeah. And we also have some of our partners that we work with on the control side are actually located in Canada, so they're very familiar with those CSA requirements.
So these units, as John briefly touched on there, a lot of hot oil heaters, a lot of regen gas heaters. Those are single phase units in the helical coil. We have used these occasionally for two-phase processes. And these skid heaters, we typically see around 5 million BTU up to around 50 million BTU. Theoretically, we can go bigger, but we're trying to provide a compact, like we said, package heater. So anything above that, about 50 million BTU absorbed duty range, it gets so large a diameter that it's hard to ship as a single piece. And when you start shipping multiple pieces, obviously your field costs start going up. So we start looking at different arrangements when we get to the larger units. Waste heat recovery units, that is a hot topic up your way. So again, like John talked about, we're trying to pick up any extra heat from your system. We typically put these on the back end of turbines, compressors, diesel engines on the exhaust stream there. There's a lot of heat there coming off, usually anywhere from 800 to probably 1200 degrees on the high end of your exhaust. So we put a horizontal flow unit through there. Skip to the next slide there. It usually comes through a silencer either right off of your exhaust, or in this picture in the middle there's a diverter key where you can divert the exhaust gas either vertically up the bypass stack or over to the unit, which contains the process coil. So that silencer can be either mounted downstream of the diverter key as it's shown there. You can mount it on top of the bypass as well. Depending on that's more of a customer preference there.
And these are good applications too. In lieu of putting in it, I hate to not sell direct fired heaters, but in lieu of direct fired heaters, if you have that waste heat stream that's essentially being lost to the environment, there's hot oil applications where you could use that exhaust to preheat that oil, as opposed to putting in a dedicated heater for your hot oil system. Just some things to look at there.
Most common is hot oil, but like I showed there, glycol, we have a few hot water heaters on offshore platforms, and then we've seen some crude as well. Go ahead, there's one more slide just to show the arrangements. So the previous slide was a vertical flow, but we can also just maintain that horizontal flow if plot space, or even if it's just not a large unit, sometimes that horizontal flow is the way to go.
And we can get real creative. We did some work with Phillips once a few years back with was a bit of a spaghetti ductwork mess getting around piping racks and getting between the equipment and the waste heat coil itself. So we can do whatever, we can find a way.
And we can even do these offshore. So there's, if there's a way, we'll work with you to find it.
Yep.
So, or I guess we're getting close here. It looks like we overran our time frame just a little bit. We hope to get
we do like to talk about heaters.
A few questions here. I don't know if Garth has been collecting questions towards the end of this.
Yeah, great job, guys. That was fabulous. I know it's probably really hard to compress everything into a 45-50 minute presentation with what you guys know and what's important, but you guys did that was a fabulous job. Other than that, I think we might as well wrap things up here. And from that, again, thanks guys. I really appreciate this. We meant to do this even last year, so sorry it took so long to get this out and introduce you guys to everybody in our territory, but it was a fabulous job. Really appreciate it, and we'll be in touch. So
thank you, Garth.
Yeah, thanks everybody. Appreciate it. Bye-bye.